Okay, now we are ready for lesson 19. So we're continuing with end behavior. And remember, end behavior is associated with horizontal asymptotes. Quite literally, when we say end behavior, we're talking about what happens to the ends of graphs as they approach positive or negative infinity. And when things are going to positive and negative infinity, they're approaching a horizontal asymptote sometimes. So in the case of rational functions, we're going to have a horizontal asymptote. So when we talk about end behavior, we're talking about the horizontal asymptote. We learned one method in lesson 18 where we separated the numerator with the denominator. We had something like x plus 7 over x. That was my function. So we learned how to do x over x plus 7 over x. And that became 1 plus 7 over x. And so this was our horizontal asymptote right here. This time, we are going to rewrite it in this notation, which we did up here, right? We did the same thing before, except our division is going to be a little more complex. We're not going to just be able to separate anymore. Instead, we're bringing back our long division, our polynomial long division. Yay! So over here, you have your typical example using numbers, right? If we took 2,775 and divided it by 11, and you can see that down here, that would be 252 and 3/11ths. So how did you get that? You put the 2,775 inside, you did division, dividing it by 11, you got 252, and then what is the 3 coming from? That's the remainder, right? So we have here, if you want to look at vocabulary, sorry, let me erase some of this. So if we have vocabulary words, then this right here is called our remainder. This right here is called our quotient. What happens when you divide 2,775 divided by 11? You get your quotient, and this right here is called our divisor. So this is representing your quotient, this is representing your remainder, and I'm guessing this probably should have been a D for divisor, but that's okay. So here you can see this is our quotient, this is our remainder, and this is what we divided by. So we're going to do the same thing, except we're going to do this with polynomials. So what would happen if I took 2x cubed plus 7x squared plus 7x and divide it plus 5 and divide it by x plus 1? So we're going to do the box method up here, right? So I'm going to go ahead and get that set up. So I have my x plus 1. And now I need to create this equation. So you can't go forwards and backwards because we are going to have remainders. So you cannot put the 5 over here on the right-hand side. It's not possible. You're going to have to start with your 2x cubed and go forward from there. So I'm putting in my 2x cubed, and now I'm going to say to myself, x times what will give me 2x cubed. So hopefully you're saying to yourself, oh, that's going to be 2x squared. And then I'm going to multiply 2x squared times x is 2x cubed, and 2x squared times 1 is going to give me what? So that is going to give me 2x squared. Now I need my 2x squared and this other diagonal right here to add up to 7x squared, right? So those need to add up to 7x squared. So what needs to be in its diagonal? Well, hopefully, oops, you're saying that needs to be a 5x squared. So 2x squared plus 5x squared gives me my 7x squared. So that works. So now I'm going to go back and I'm going to say x times what number will give me 5x squared. Hopefully you are saying to yourself, that's going to be 5x, right? 5x times x gives me 5x squared, and 5x times 1 gives me 5x. So I'm going to put that here. And then I have to do this again. So my diagonal, this 5x plus this number here has to give me this 7x, right? So what does that need to be? Well, just coincidentally, that has to be a 2x, right? Because 5x plus 2x is 7x. So now I need to say to myself, x times what will give me 2x. So that value is going to be 2. And then 2 times 1 also gives me 2. right? So 2 times 1 gives me 2. And then my last thing I'm going to do is look at my remainder. So this right here needs to be, these two right here need to add up to be your remainder. So they need to add up to give me a 5. This is a plus 5. I just covered it up. So those two things need to give me a plus 5, which means I have a remainder of 3. So notice we used 2775, just like we have over here. Notice we have a 1 and a 1. Notice we have 255, but 252 with a remainder of 3. So they're lining up. So now how do I write that? Well, if I took 2x cubed plus 7x squared plus 7x plus 5 and divided by x plus 1, I would get 2, actually I'm going to use the proper colors, 2x squared plus 5x plus 2. This is my quotient up here, right? So this is my quotient. And then I'm going to add the remainder of 3, and I divided the whole thing by x plus 1. Right? So I divided by x plus 1, just like here I divided by 11, so it's my remainder over what I divided by. So this would be my final answer if I did this long division in this form up here, which is what our ultimate goal is to understand how to do that long division so we can get it in this form up here, where this is the quotient, and then you put your remainder over whatever your divisor is. Now, how could we do it this way? It's also the same as saying, okay, if we multiplied x plus 1 times 2x squared plus 5x plus 2, and then we added our remainder of 3, we would get this 2x cubed plus 7x squared plus 7x plus 5 as a result. Okay, now how are we going to use that to identify our horizontal asymptote? Or we have one other type of asymptote that we will introduce you to. It's called the slant asymptote or the oblique asymptote. So we're going to look for some patterns here in this next section. Therefore, we're trying to get you to see those patterns by looking at the degree of the numerator, and NUM is just, I'm trying to say numerator, and this is the degree of the denominator. So DEM is denominator. So what is the degree of the numerator? What is the degree of the denominator? Well, if you look here at g of x equals -5 divided by x plus 2. That's a rational function. And if we don't have an x here, that means it's x to the 0, which means my degree in my numerator is 0, and my degree in my denominator is equal to 1. Right, so we're just going to compare degrees later. So right now I have a degree in my numerator, which is 0, a degree in my denominator, which is 1. If I want to rewrite I'm going to rewrite all of these functions in this form right here. And notice in order to do that, I just demonstrated how we're going to do that, and we have to do long division. But if your degree in your numerator is less than your degree in your denominator, you can't do long division. There's nothing to divide. If we have 3 divided by 7, this number is less than this number. Can I go 3 divided by 7? You could, you're just going to get a decimal, but we can't, we're not going to divide it with polynomials. There's nothing to do. So we have 0 minus 5 divided by x plus 2. Okay, what is the significance of this 0 right here? Well, this, remember, is indicating our horizontal asymptote. And I'm putting the 0 there just to show you that there is a horizontal asymptote, but that horizontal asymptote is y equals 0. So this has a horizontal asymptote at y equals 0. Therefore, my end behavior is as x approaches plus or minus infinity, g of x approaches what? Well, it approaches the horizontal asymptote, which is 0. So this all goes together right here. Okay, now h of x is a little bit different. So h of x, we actually have to do the long division. We have a degree in the numerator, that degree is 1. The degree in the denominator, that degree is also 1. When those degrees are the same, we can do long division to figure out how to rewrite it in this form right here. So remember, we're going to make our little box. I'm going to put my denominator of x plus 2 here. Extend this a little bit to continue with my box. I'm making it very small because all I'm trying to create is this 7x minus 5. So the first thing I do is put the 7x in there. So if I put the 7x in there, then what is going to go up here? Well, this is going to be a 7. 7 times x is 7x, and 7 times 2 is 14, right? So I get my 14, except I don't want it to be 14. I need to get this to be minus 5. So I need to get this diagonal piece to become minus 5. So what is my remainder going to be? So this needs to be the remainder right here. So 14 plus my remainder has to give me negative 5, right? These diagonals need to add up to give me my remainder. Therefore, what is my remainder? Well, hopefully you're saying your remainder is negative 19. Negative 5 minus 14 is going to give me negative 19. So now how do I write that? Well, I did my long division. This number up here is my quotient. So h of x equals 7. That's my quotient, plus the remainder. But when the remainder is negative, I'm just going to put minus the remainder divided by whatever my divisor is. So whatever my denominator is over here. So again, what I get up here is my quotient. That's what I put here. And then my remainder is what I put in the numerator of that second part. Now, what do we know? What's so special? Why are we doing this long division? Because your quotient is your what? Your quotient is your horizontal asymptote. So now we know that we have a horizontal asymptote at y equals 7 this time. So y equals 7. And what is my end behavior going to be? My end behavior is as x approaches positive or negative infinity, all of the y values are approaching what? They are approaching 7. Again, why? Because this value here is 7. Therefore, that's indicating what my end behavior is going to be, and that's also indicating what my horizontal asymptote is going to be. Now, this next one, I don't like the example, so I'm asking you to change it. I want you to remove this squared, and I want you to remove all of this right here. So I literally just want my j of x to be 3x plus 7 over x plus 2. I just want to do another example like this. So I'm asking you to kind of scratch that out or rewrite it right below and say j of x equals 3x plus 7 divided by x plus 2. So if we look at this, this has a degree of 1, this has a degree of 1. So once again, the degree of the numerator is 1, and the degree of the denominator is 1. It is not in this form up here, so I need to do long division to get it in that form. So I have to create my box over here. I put my denominator of x plus 2 out here on the left-hand side, and then I take this first value, I need to get a 3x, so I'm going to put this here on the inside, so that needs to be 3x. So now I say to myself, 3 times x gives me 3x. So I already know my j of x equals, and then I have 3. And then 3 times 2 is equal to 6. Of course, what do I know? I know that this diagonal needs to add up to my remainder. So this is my remainder right here. I can put it in R. So 6 plus R needs to give me 7. right? So it needs to provide and produce that value of 7. So what is my remainder going to be? Well, I subtract 6 on both sides. So my remainder has to be 1. So my quotient is 3. And then because my remainder is positive, I'm going to put plus 1, and then I divide it by whatever I have as my denominator over there. So what do we have? We have this is our quotient. Our quotient is up here. This is our remainder. Our remainder goes here. And of course, this is what we are dividing by. So that goes here. But this quotient is crucial. That's a very important because that produces your horizontal asymptote. So your horizontal asymptote, where is it? You have a horizontal asymptote of y equals 3. What does that mean? That means your end behavior as x goes to positive or negative infinity, all of your y values in the function j of x will approach 3. So hopefully you are seeing this connection that the quotient is relative to your end behavior, which is also connected to your horizontal asymptote. The other thing I want you to notice is that these degrees were both 1. These degrees were both 1. So when the degrees are both 1, you can find that horizontal asymptote. What was the horizontal asymptote? Well, this coefficient is 3, this coefficient is 1, and 3 divided by 1 is 3. This coefficient was 7. This coefficient is invisible. It's in front. It's a 1. And 7 divided by 1 is 7. So when your degrees are the same, you can find your quotient or your horizontal asymptote by taking the coefficient in front of the variable in the numerator and the coefficient in front of the x in the denominator and dividing them to get that quotient or that horizontal asymptote or wherever the end behavior is approaching. That was a lot in this one example. We'll summarize it at the end. There's a worksheet that the substitute will hand out to you that you can do a little summary. If you don't have it, then you'll just have to flip over your book at the back and write it all down. But I think you should be getting that worksheet. Okay, here are a few more examples I want you to try. Again, this highlighted portion I want you to cross out. So this one is unique. This one's a little bit more complex. This time, if you look at the degree in the numerator is 2, and the degree in the denominator is 1. Notice the degree in the numerator is greater than the degree in the denominator. When that happens, so when the degree in the numerator, we'll summarize this later, is greater than the degree in the denominator, so this is a greater than symbol, then you end up with something called a slant or an oblique asymptote. And I'll show you what I mean when we do our long division. So we have to do our long division in order to get it in this form right here. So we're going to have a little bit bigger box. So I have my denominator. My denominator is x plus 2. And I'm going to start with 3x squared right here. So in order to have a 3x squared, I've got to multiply by 3x. 3x times x is 3x squared. 3x times 2 is 6x. So I have that right there. So far, so good. Then I'm going to look at my diagonal. So these two right here need to add up to give me 7x. So what needs to go in that diagonal? Well, that would be 1x. And so if that's 1x, this is going to be a positive 1 up here. 1 times x is 1x, and 1 times 2 is 2. But I need to have this diagonal add up to give me -5. So remember, this next column, I don't know why my thing keeps moving, is associated with the remainder. So 2 plus the remainder has to produce a -5. So I subtract 2 from both sides and I get that r must equal -7. So 2 plus -7 is equal to -5. So I have a remainder of -7. Now, if I'm going to write it in this form, That means k of x is going to equal what we have up here. Now it's just a little more complex, but that's okay. We have 3x plus 1. I'm going to write that in red so we color coordinate. So 3x plus 1. And then I have my remainder of -7. And then I divide it by whatever I divide it by over here. So this part right here is not as simple as the other one. And if you look at that, y equals 3x plus 1, what is that an equation of? That's an equation of a line. And if you were to sketch that line, right, if you were to quickly sketch that equation of a line, it would go through 1 on the y-axis and it would have a positive slope, so it'd be pointing in this direction. That's actually an asymptote. It's called a slant asymptote. So your graph is going to approach that line. So that's going to change your end behavior. We don't have a horizontal asymptote. It doesn't approach something specific. Instead, we have something called a slant asymptote. And that slant asymptote is just y equals 3x plus 1. It is the equation of the line. So your graph might approach this and it might approach this, something like this. So they're really interesting. You can graph this in your calculator and see what it looks like if you want to have a little peek at what it looks like. So I'm not sure I sketched it, I was just making a sketch. But then what happens to our end behavior? Well, we still have to write our end behavior as x goes to positive or negative infinity. If this is the graph of the equation of a line right here, then as x gets bigger and bigger and bigger, and this is the line that has to eventually follow this line, then your y values are also getting bigger and bigger and bigger. But we can't put these together anymore. They're going to be separate. So I need to separate this, and I'll tell you why in just a minute here. So first, as x goes to positive infinity, follow the slope of the line right here. This was your oblique asymptote and it has a positive slope. That means as x gets bigger and bigger and bigger, it's going to be going up because it's going to follow this slant asymptote or this oblique asymptote. It's getting closer and closer to that line, and that line is going towards positive infinity. If I go the other direction to negative infinity, so as x gets more and more negative, it's going to follow this line, and this line is going down. So then my k of x will approach negative infinity. So this slant asymptote, your graph is still going to see. So go ahead and graph it in your calculator, see what it looks like, so you can see what I mean by these two end behaviors right here. So when you have a slant asymptote, you need to separate your end behaviors. So you need to write them separately. You can no longer put them together, but you can put them together for a horizontal asymptote, but not for a slant asymptote. This last one, your degree in your numerator is 1 and your degree in your denominator is 3. So when your degree in your numerator is less than the degree in the denominator, then you have a horizontal asymptote of y equals 0 every single time. And you don't need to do long division because your numerator is less than your denominator. So we're not going to do any long division. It's already in this form. But you could say m of x equals 0 plus x plus 2 over, and then all of that stuff here. So we don't need to do anything at all. It just has this invisible 0 in front, which is indicating what your horizontal asymptote is, which is also indicating what your end behavior is approaching, right? So it's going to approach 0. So when your degree in your numerator is less than your degree in your denominator, you have this 0 you could add there, which is your horizontal asymptote and your end behavior. I know that's a lot. You've digested a lot. You're going to have to maybe go back and re-listen, go back, look, get out your calculator, graph, so that you can practice, because all of these things will be on the assessment because we're trying to assess these learning targets. So it says I can find end behavior of a rational function by rewriting it. So you do long division and rewrite it this way and realize that this is the horizontal asymptote, which is also your end behavior of what that graph is actually approaching. So your summary, what is a vertical asymptote? Hopefully you know the vertical asymptote is x equals a, and a is what makes your denominator 0. So it's whatever makes your denominator equal to 0, then that's going to be your vertical asymptote. So if I had 3 over x plus 1 as your function, then you could say, okay, I'm going to make x plus 1 equal to 0 and x equals -1. So that's my vertical asymptote because it would make this denominator equal to 0. For your horizontal asymptote, if the degree of the numerator is equal to the degree of the denominator, go back and look at your notes. We did 2 examples like that. If the degree of the numerator is equal to the degree of the denominator, then the coefficient in the numerator divided by the coefficient in the denominator. So the coefficient in front of your x, right? That's the value in front of your x. That will be your horizontal asymptote. That will be the value of the horizontal asymptote. So it'll be y equals the coefficient in front of the numerator divided by the coefficient in front of the denominator. I'm sorry, that is so incredibly sloppy. I just don't have enough space. It's hard for me to write on whatever I'm writing on right now. So if I said f of x equals 3x plus 5 over x minus 1, this numerator has a degree of 1. The denominator has a degree of 1. We take the coefficient, which is 3. So my horizontal asymptote is whatever this coefficient is 3, this invisible coefficient is 1. So I have a horizontal asymptote of y equals 3, because 3 divided by 1 is equal to 3. So that's my horizontal asymptote, and that is also my end behavior. So as x goes to positive or negative infinity, y would go to 3. So write yourself an example, or you can say whatever, however you want to describe this number in front of x. That's the way it would be. If this was a 5, right? If this happened to be a 5 right here, we would have 3 divided by 5, and that would be a horizontal asymptote of 3/5. Okay, if your degree in your numerator is less than the degree of the denominator, we did 2 examples like that. If your degree in your numerator is less than your degree of your denominator, then you have a horizontal asymptote of y equals 0 every single time. And your end behavior would be as x goes to positive or negative infinity, y would approach 0. And then we have our slant asymptote. Your degree of your numerator needs to be 1 more than the degree of the denominator. We just did that as our next to last example. And remember, what you end up having is some kind of y equals, I think we ended up having 3x plus 1, but it's an equation of a line, right? You end up with an equation of a line, and then you have to look and see if that slope is positive or negative. If the slope is positive, just envision that. That means your line's going this direction. That means as x goes to positive infinity, your y value is going to positive infinity. As x goes to negative infinity, your y value is going to negative infinity. If you had a negative slope, it was -3, then your graph would look like this. So it'd be as x goes to positive infinity, y goes to negative infinity because it's going down. And as x goes to negative infinity, y would go to positive infinity because the slope is this direction. So if you went to the left, it would be going up. But if you went to the right, it'd be going down. Again, graph it, check it out. This was a long lesson. There's a lot here, and you need to know how to do that. Now there's one more page for you to practice. So if you didn't get this, hopefully your substitute has given it to you, or you can just write it on your notebook or on a scratch sheet of paper, or just use a marker and put it on your table, or if you're at home. But go ahead and practice this. Decide, is the degree of the numerator, so top is numerator, right? So it's numerator divided by denominator. So I haven't been saying top and bottom, I've been saying numerator and denominator. So top, bottom. So is it equal to, less than, or greater than? That's what you're putting here, equal to, less than, or greater than. And then once you figure that out, you can determine the end behavior and the slant or horizontal asymptote. So pause, try this on your own, and then check your work when you're done. Then you can listen and check your work. Okay, so this first one. The degree in my numerator is 1, the degree in my denominator is 2, so the degree in the numerator is less than the degree in the denominator. Therefore, I do have a horizontal asymptote, and it's automatically a horizontal asymptote at y equals 0, or you could use f of x equals 0, that's fine. In your end behavior, you should say as x goes to positive and negative infinity, you should use that function notation. Your function is approaching 0. So that's what we have. You can say y equals 0, you can say f of x equals 0 for your horizontal asymptote, but here in your end behavior, you should say that the function is approaching 0 by using the function's title, which in this case is f of x. In number 2, the degree in the numerator is 1, the degree in the denominator is 1, so that is equal. That means in order to find my horizontal asymptote, I take the coefficients. So I'm going to do 9 divided by 3. Well, 9 divided by 3 is 3. So it has a horizontal asymptote at y equals 3. And so once again, your end behavior is just as x approaches plus or minus infinity, then k of x is approaching 3. This last one is a little more complex because the numerator's degree is 2 and the denominator's degree is 1. So the numerator's degree is greater than, so therefore it is going to have a slant asymptote. You are going to have to do long division to figure out that slant asymptote, and then you have to see if the slope is positive or negative. So I'm going to do 2x squared. Um, I'm going to do that really quickly. I have x minus 2. So 2x squared, I have 2x. So that's going to be 2x squared minus 4x. So I need to have a 3x here. So I'm going to have a plus 3. So this is really all you need. The remainder doesn't matter. So, but if I did that, it would be -6, and I'd have my remainder. So my remainder would be 3. But your slant asymptote is just this equation of a line, which is 2x plus 3. Because this slope is positive, your line looks like this, which means as x goes to positive infinity, r of x is also going to go to positive infinity because as you went to the right, your y values went up. And then as x goes to negative infinity, your r of x goes to negative infinity because as you went to the left, the y values went down. So it's all relative to your slope to how you're going to answer this end behavior here. I hope this helps. I know it's long, but please make sure you are practicing and reviewing it because when we come back, we have a whole different topic after the October break, and then we'll have a review and then your test. Reach out if you have questions or watch some of the video links that are in our lesson as well. Bye. Have a good October holiday.